I set up that voltage divider to give me plus or minus a volt. I'm not getting even a tenth of that. At least the output current is tracking it. I suppose that's good. Hi, I'm Kevin. Welcome to my cave. Last time we were looking at op-amp current sources and managed to build one that was able to source some real current, over an ampere precisely. That took us on rather an adventure through the thermal calculations needed to keep our circuit from going up in smoke. The chief remaining drawback to our last couple of circuits is that they're single-ended. They can source current, or sink it if we swap P-channel MOSFETs with N-channel ones and PNP transistors with NPN, but they can't both push and pull. Now I want to look at some bidirectional sources. The first one I want to cover is a classic textbook circuit, the Howland current pump. That's partly because a few viewers asked me to cover it. For reasons we'll see in this episode, I had half a mind to skip it, but it's too brilliantly simple an idea to ignore completely. The Howland current pump is named for Bradford Howland, another intriguing character of the early days of electronics. Howland was a child prodigy, graduating from Purdue with a degree in electrical engineering in 1945 at the age of 17. After completing his education with a master's degree from Harvard and a doctorate from MIT, he embarked on a long career with MIT, first in the research laboratory in electronics, where he designed circuits for experiments on captured German V-2 rockets and contributed to research in neurophysiology. Later, Howland moved into Lincoln Laboratories and shifted his focus from electrical engineering to optical engineering. He worked on classified projects for imaging satellites. While working in optics, he collaborated with his younger brother Howard in designing the first aberometer, a device for measuring optical defects in human eyes. I'm personally a beneficiary of Dr. Howland's research, since my eyes are much patched by the ophthalmic surgeons, who used aberometry in a couple of their procedures. While Howland held over 20 patents in optics, electronics, and mechanics, the Howland current pump is what he's best known for. While he never published nor patented the circuit, he communicated it to George Philbrick in 1962, and Philbrick immediately saw its usefulness. Philbrick Research started including it in the application notes for its op-amps in 1964. After retiring in 1987, Howland published a book of anecdotes from his time at the research lab in electronics, under the title Building 20 Stories. Before we continue, let me interrupt for just a moment. Longtime viewers of this channel will know that it's always free to all comers. Nothing is ever paywalled. But I do end each video asking one thing, that you take care of one another. To that end, all the advertising revenue that I earn from this channel goes to charity. The current featured charity is called Heifer International. Heifer's mission is to end hunger and poverty in partnership with the communities it serves. It begins with a seed investment in livestock or agriculture, together with mentorship to help its participants build a business. The participants, small farmers, ranchers, and female business owners, are able to learn a living income and continuously lift up their communities as they train the next generation of leaders. I'd like to ask you to join me in supporting this organization. I set a goal of $500, which is enough to give a cow to a family in need, together with training and education in how to care for her and how to access the market for her milk. I know that with the generosity of Kevin's Cave people, we'll just crush that goal. Won't you help out today? There's a link to donate, up here, or down there, or at any rate somewhere nearby. Thanks so much, and now back to the video. Howland's idea for the current pump is brilliantly simple, but most textbooks overcomplicate it by leaping to calculation. They either present it as an exercise for the student, or run through an agonizing analysis based on the nodal equations. Let's instead start the way Howland did, by reasoning about the current balance in a circuit. Howland started from the simplest possible current source, a resistor connected to a constant voltage. As long as the source resistance is much greater than the load resistance, the output current will be more or less constant. This was actually a fairly common technique at the time. The analog oscilloscope that I've been working on has a 130-volt power supply that's used in several places to allow for huge resistors in its current sources. Howland reasoned that no matter what the load impedance was, the current would induce some voltage across it. Ohm's law gives the current through the input resistor, and we can regroup the terms to get the amount by which it falls short of the desired current. What if there were some way to introduce a helping current to provide the shortfall? Since we're already looking at a simple resistor as a current source, why don't we try to provide that current with another resistor? Since the voltage appearing across the load can vary, that resistor will have to be fed from a variable voltage source. Do we have an easy way to get that variable voltage? Well, let's see what it has to be. The current through our second resistor is determined by Ohm's law, and we can split the terms. For simplicity, I'm going to assume the two resistors have equal values. I can combine this equation with what we want the current to be up above. And that's simple. We need to supply the second resistor with twice the load voltage. By this point in an op-amp course, you're probably screaming out the answer. We need a non-inverting amplifier with a gain of 2. The positive input of the op-amp goes to the low voltage, and the feedback path has to be a voltage divider with a gain of 1/2. That is to say, its two resistors must be equal. And that's really all there is to the Howland current pump. Well, mostly anyway. If you work through it for yourself, you'll find the only real constraint on the resistor values is that the ratio of the top pair has to match the ratio of the bottom pair. And what we've done is to make this circuit behave ideally with the input resistor and input voltage determining the current regardless of the load. Let's try it out. Once again, the schematics are on the project GitHub. Link in the video description. I'll choose the input resistor to get an output of 1 milliamp for an input of 1 volt. And the other 4 resistors will match. I'll use a voltage divider to get the input voltage, ranging to plus or minus 1.2 volts. And I'll let the load vary from a short circuit to 1K. What I'm seeing is not what I wanted. The output current is tracking the input voltage all right, but the input voltage isn't varying over anywhere near the plus or minus 1 volt that I wanted. And if I lower the load impedance, the input voltage is falling off with it. This is hardly any better than using a simple resistor as a current source. That's because of the first big drawback of the Howland pump. If the load resistance is tiny, there will be a negligible voltage across the load. The current through the input resistor will be the input voltage divided by the input resistance, so the input impedance will be approximately equal to the input resistor's value. Since current sources are usually driving a low impedance, this can be quite a problem. We want voltage-controlled circuits to have a high input impedance. And we don't get to choose the input resistor's value, since that's what determines the transconductance. The impedance of that voltage divider, providing the input voltage, is about 20 times the input impedance of the current source if the load impedance is low. Fortunately, we have an unused op-amp on our TL072. So we can simply rig a unity gain buffer to accommodate that. Let's make that change and test it again. Okay, that seems to be better. The output current is tracking the input voltage. I can turn the load pot up and down, and the current is fairly close to constant. Fairly close, but not dead on. Put a pin in that, I'll come back to it. Let's try a higher impedance load. I'll pull out the 1K pot and plug in a 10K one. Now I'm seeing some other trouble. As I turn up the resistance, we run into a cliff where the current starts dropping off precipitously. The same thing happens with the negative input voltage. It tracks more or less for a while, and once again drops off a cliff. Let's characterize that more closely. I'll replace the load pot with a resistor substitution box so that I've got an easy way to know what the precise load resistance is. That way I can dial in the voltage and see how it performs with various known loads. That will let me plot curves. I'll spend the next half hour or so turning knobs, flipping switches, and writing down data. When I plot the curves of output current versus load resistance for a variety of input voltages, I get some less than stellar results. First off, the output current is surprisingly limited. If I ask for a milliampere out in either direction by giving the circuit an input voltage of a volt, the current is already dropping off when the load resistance hits 5K. That's less than 5 volts of the load resistor. The same thing happens at smaller currents. If I ask for half a milliamp, the fall-off comes later, but it's still less than 5 volts across the load. But if we recall how the circuit works, it should have been obvious this was going to happen. Remember that the voltage of the op-amp output was twice the load voltage. And I'm not even using an op-amp with rail-to-rail outputs. Indeed, if I assume that the op-amp will swing plus or minus 9 volts, and plot the currents I expect to see, it matches closely enough to convince me I'm on the right track here. The other thing I notice is that the lines all slope away from the horizontal, so the output current is not quite constant. It gets worse the higher the output current gets. At a milliamp, when the current hits the limit, we're looking at an 8% error. And I was using high-quality 1% resistors from the same batch, picked from adjacent spots on the tape. They all matched to within about 0.5%. The math is kind of tedious here, but recall that we had a requirement that the resistor ratios have to match. It turns out that if they don't, the output impedance, which is ideally infinite, will be determined by the feedback resistor and the mismatch ratio. Another imbalance can come from the input offset voltage, or the common mode rejection ratio of the op-amp. These effects are why we see slightly different slopes for positive and negative currents. Unfortunately for us, there's no easy way out of this issue. If we want a precision current source, we're going to have to use a low offset op-amp, probably a chopper stabilized one, and more precise resistors than 1%. If we want to handle worst case tolerances and get better than 1% tolerance on the output current, we're most likely looking at 0.01% resistors. Those are readily available, at a price. When I check my distributor, they're over $1 a piece in hobbyist quantities, and come down only to about 75 cents, even if you're buying them by the 5,000-piece reel. By contrast, ordinary 1% ones go for a few pennies each if you buy 100, and a fraction of a cent by the reel. The alternative would be to trim one of the resistors, but then we would probably need extra circuitry to apply a test signal to adjust the trim, and of course we have to pay for the trim pot. So to summarize, the Howland pump has solved 2 of our problems. It can push current in either direction, and its inputs are fully differential. If an upstream circuit has a different idea of what ground means, that's not a problem. And we can get a negative transconductance just by interchanging the two inputs. On the other hand, this circuit's input impedance is horribly low. It usually needs a buffer upstream, and at low load impedances, that buffer has to be able to deliver most of the output current. Its voltage compliance is poor. The output voltage caps out at less than half the op-amp supply voltage. And its output impedance, we just saw, is horribly sensitive to component tolerances. If they vary in the wrong direction, the incremental output impedance can even be negative. A change in the load can either increase or decrease the output current depending on the direction of the imbalance. All of these drawbacks are why you see the Howland pump much more often in textbooks than you do in real life. There's a circuit that the legendary Bob Weidler invented, which takes care of the input impedance and voltage limitation, and gives us a cheaper path to deal with the imbalance issues. I'll get into that one next time in this series. I hope you'll stay tuned for that, and maybe tell the YouTube algorithm that you want to see it when it drops. Until then, stay safe, stay healthy, stay curious, and please take care of one another. Bye! And its output impedance, we just saw, is horribly sensitive to control. And its output impedance, we just saw, is horribly sensitive to component tolerances. And its output impedance, we just saw, is horribly insensitive. And its output impedance.